All right, today we're diving deep into one of the most important and maybe one of the most famous equations in all of physics. This is the rulebook for the quantum world, a place that, well, it pretty much defies all common sense. If you've ever heard that a particle can be in two places at once and wondered how that's even possible, well, the answer starts right here. Let's get into it. So what on earth does that mean? Let me put it this way. You know how Newton's laws can predict the exact arc of a baseball as it flies through the air? The Schrödinger equation is trying to do the same thing, but for the tiniest things in our universe, like a single electron. It's basically the master formula that tells them how to behave.
And that is the big question, isn't it? Because, you see, in the quantum world, particles are nothing like baseballs. They act like waves. They exist in this weird haze of probability. So how can a single equation possibly describe all of that strangeness? Well, that's what we're here to find out.
Okay, so our first step is to pop the hood and see what we're working with. We're going to break this equation down piece by piece, symbol by symbol, and you're going to see that it's not nearly as scary as it looks. Each little part tells a piece of the quantum story.
And there she is, in all her glory. This right here is the time-dependent Schrödinger equation. This is the big one, the version that describes how a quantum system changes from one moment to the next. I get it, it looks like a jumble of Greek letters and weird symbols, but trust me, we're going to decode this thing together. Let's start with the absolute star of the show, this symbol right here, psi. This is the wave function, and it is the heart and soul of this entire equation. Think of it like a particle's complete digital file. Absolutely everything we could possibly want to know about that particle, its energy, its momentum, where it might be, it's all bundled up inside this one mathematical object. Next up, we've got this H with a little hat on it. This is called the Hamiltonian. Now, in quantum mechanics, anything with a hat is called an operator. It's basically an instruction, a command to do something to the wave function. And the Hamiltonian's job, its job is to figure out the total energy of the system. It adds up its energy from moving around, that's kinetic energy, and its energy from its situation or position, which is potential energy.
Now, you probably remember I from math class as the square root of -1, right? The imaginary number. Well, in this equation, it's not just some weird mathematical curiosity, it is absolutely critical. It's the key piece of the puzzle that lets the equation describe things that act like waves, which it turns out is exactly how particles behave at the quantum level. And finally, we have this little symbol, h bar. This is the reduced Planck's constant. At the end of the day, it's just a number. An incredibly tiny number, but it's maybe the most important number in this whole field. It is the fundamental constant that sets the scale for the entire quantum world. Seriously, if this number were 0, quantum mechanics just wouldn't exist. So that big equation we just saw is perfect for describing how things change over time. But a lot of the time, physicists are looking at systems where the energy is nice and stable. It's not changing. And for that, thankfully, they use a much simpler, sort of timeless version of the equation.
And you can see them right here, side by side. On the left, there's our original equation, the one for systems that are evolving. But look at the one on the right, so much cleaner. That's the time-independent version. We use this when a system's energy is constant. You'll notice the Hamiltonian and the wave function are still there, but now we've got a brand new letter, E.
This E, as you might guess, stands for energy. But here's the catch, it's not just any energy. In the quantum world, a particle can't just have any random amount of energy it wants. It's restricted to very specific, discrete levels, kind of like the rungs on a ladder. You can be on one rung or the next, but you can't be in between. These allowed energy levels are called eigenvalues, and this simple little equation is the key to finding them. Okay, so we've taken apart the math, we know what the simples mean, but this leads us to the biggest, the weirdest, and honestly the most profound question of them all. We said the wave function contains all the information, but what does that information actually mean for the real world? Right. Does it tell us exactly where the particle is at any given moment the way Newton's laws can pinpoint a baseball? The answer, and this is where it all gets crazy, is a huge no. And this is where quantum mechanics really veers off into the weird and the wonderful. And here's the secret. This is the big reveal. The wave function itself doesn't tell us where the particle is. But if you take its magnitude and you square it, you get something amazing. The precise probability of finding that particle at any given spot in space. The equation doesn't give you a certainty, it gives you a beautiful map of possibilities. And this leads to a rule that just makes perfect sense. If you add up the probability of finding the particle everywhere it could possibly exist in the entire universe, the grand total has to be 1, 100%. That's what this 1 on the slide represents. The particle has to be somewhere after all.
So we have this powerful equation that only gives us probabilities. And you might be sitting there thinking, well, what good is that? It turns out, predicting possibilities is an incredibly powerful tool. By solving this equation for different scenarios, we can predict how quantum systems will behave with an accuracy that is just mind-blowing.
Just look at a few of these examples. If you solve the equation for a particle just floating in empty space, it predicts it will act like a simple wave. But trap that same particle in a box, and the math tells you its energy has to be quantized. It's stuck on those specific energy rungs we talked about. And for every one of these systems, real-world experiments have confirmed that the predictions are spot on. So here's the main takeaway. From this one central equation, our entire understanding of the microworld flows. Even though it's all about probabilities and chances, it is one of the most successful and precise theories in the history of science. It's the foundation for how we understand atoms, how chemistry works, and the technology you're using right now, from lasers to the computer chips that run our world.
And that kind of brings us to our final thought for the day. The equation works beautifully, but it leaves us with this huge, profound question. It suggests that at the deepest, most fundamental level, our universe isn't some predictable clockwork machine. Instead, it seems to be a world built on probability, on chance. What does that really mean for the nature of reality itself? That's something to think about.